Hello everyone, my name is David Brown. I'm Assistant Professor of Mechanical Engineering at Vanderbilt University, where I lead the Advanced Robotics and Control Laboratory. Our works aim to advance the foundation of robotics by optimization-based control methods, innovative actuators, and a new theory of human performance augmentation. In this talk, I will discuss emerging compliant actuation concepts in robotics and how we can use them to build better human augmentation devices. But what is human augmentation? So this question could be answered by a simple inequality relation, which suggests that a human using a device can do more than the human without a device. One way to imagine human performance augmentation is to consider an energetically active robot that supplements muscle power with external energy. The Hardiman project in mid-60s was one of the first modern attempts to develop an exoskeleton robot that can amplify human limb force 25 times. Although the robot was never born by a human, the project identified key challenges in augmenting human performance using powerful actuators that require a large and heavy power source. Another way to imagine human performance augmentation is to consider energetically passive devices that are human-powered. Examples of human-powered energetically passive devices are springs, ice skates, and bicycles. Springs can support the body and they can also mitigate collisional energy losses as the foot touches the ground. But no spring enables the runner to run faster than a simple running shoe. On the contrary, ice skates enable 25% speed boost, while cyclists can nearly double the top speed of running. So what makes the difference between passive devices if none of them can supply external energy? To answer this question, we consider the experimental data of human-powered locomotion, running, ice skating, and cycling. We observe a linear empirical relation between the top speed and the time available for the legs to supply energy. Ice skates can maintain ground contact longer due to the sliding contact of the blades. The bicycle allows the legs to do work continuously in the air 100% of the total cycling time, as opposed to the 50% in ice skating and the only 20% in running. Therefore, increasing the speed in running can be achieved by increasing the time available for the legs to supply energy. This conjecture is supported by a simple physics-based analysis of the air resistance limit in human-powered locomotion. Assuming that the average power per step is proportional to the time available for the legs to supply energy, the maximum speed at the air resistance limit will be proportional to the cube root of the time available for the legs to supply energy. But what kind of device should we use to enable the legs to supply more energy? We have recently shown that a device as simple as a spring could enable the human to supply more energy in running. This could be done by a human supplying energy, compressing the spring in the air, and subsequently releasing the stored energy as the spring touches the ground. This is similar to pedaling a bicycle in the limit approaches the benefit provided by the bicycle. But even if the legs are only supplying energy 60% of the time instead of the continuous limit of 100% in cycling, the running speed of the augmented running could increase 50% compared to natural running. The same idea can be generalized to other types of human-powered locomotion. For example, we have recently shown that if the human is augmented with a spring that has sufficient energy storage capacity, then the jump height can be increased by repeated jumping, where the energy for subsequent jumps is provided by the human compressing the spring between jumps. In both cases, the spring used to augment the human is not a simple spring, but a special type of variable stiffness spring, a spring that can change its stiffness without supplying energy. Energetically passive variable stiffness springs bring us to the concept of compliant actuation in robotics. Compliant actuators are actuators that combine motors with springs. The motor supplies the external energy, while the spring stores and recycles the energy. There are different types of compliant actuators. Here, from left to right, we can see the variable stiffness actuators, the series elastic actuators, and the emerging class of human-driven variable stiffness spring actuators. One of the most general compliant actuators is the variable stiffness actuator that uses two motors. One of the motors, the large motor, is used to supply energy. This motor requires a hefty power source. The other motor, typically a small motor, is used to modulate the stiffness of the spring embedded into the actuator. The small motor can only supply a limited amount of energy and can be powered using a small power source, a small battery. Variable stiffness actuators can provide safe human-robot interaction, safe robot-environment interaction, and can be used for optimal resonance-based actuation, something that is shown in the video here. However, the extra motor can make variable stiffness actuators bulky. One way to avoid the extra motor is to use the conceptually simpler series elastic actuators. Series elastic actuators can still modulate stiffness using feedback control. This requires more energy but doesn't require an extra motor. However, both variable stiffness and series elastic actuators use a large motor and require a hefty power source to supply a significant amount of external energy. But the human body is an extraordinary power source, and to significantly enhance human peak performance, it is not necessary to supply external energy. For example, a world-class cyclist can provide 19 watts per kilogram continuous power, enough to nearly double the top speed of running. Variable stiffness spring actuators are an emerging class of compliant actuators where the human supplies the energy. This is a conceptual change compared to variable stiffness actuators and series elastic actuators. This conceptual change could enable human augmentation without powerful actuators and hefty power supplies. The question which remains is, why should the stiffness of the spring change? The reason is fundamental and can be explained by considering the example of running with a spring leg. According to the impulse-momentum relation, the spring force required to redirect the motion of the body is inversely related to the ground contact time. However, the ground contact time reduces with increasing running speeds. Assuming that the ground contact time is inversely proportional to the running speed, a good assumption up to the top speed of ice skating, the force must also increase with the running speed. Because the force is proportional to the square root of the stiffness at the same spring deflection, the stiffness should also increase as the runner picks up speed. This is similar to switching to a higher gear as the cyclist rides faster. This example can be extended to other tasks, for example, repeated jumping. Although springs have been imagined to augment human performance with patents dating back to 1800s, it has been only more recently that simple exoskeleton devices that use or mimic springs could reduce the metabolic cost of walking and running. But reducing metabolic energy cost is not analogous to increasing peak performance. Early bicycles used wheels and seat and could reduce the metabolic cost of the human, but could not allow the human to move faster than by running. Only after the invention of the pedal and the variable gear transmission mechanism could a cyclist move significantly faster than a runner. In our example of running, the variable stiffness spring is similar to a pedal and the gear transmission mechanism in a modern bicycle, because it allows the human to supply energy even if the legs are in the air, similar to the pedal, and because it also accommodates increased speeds by increasing stiffness, similar to when switching to a higher gear. The development of robot exoskeletons are currently in the early stage of a new promising technology, when a number of different devices are built and tried, hoping to find one that really works, somewhat similar to what has been done to develop the modern bicycle. However, fundamental theoretical investigations have not been exhausted. Theoretical investigations to guide and speed up experimental explorations aiming to develop the 21st century exoskeleton technology. Our theoretical investigations show that variable stiffness springs could play a key role in a new generation human performance augmentation devices that could enable us to bypass set biological limits of human mobility.